Hello students, welcome to lecture 12 of this course. In the last 5 lectures I have discussed about rotational spectroscopy, vibrational spectroscopy, rotational vibrational spectroscopy and Raman spectroscopy. We have looked at both theory and application of these spectroscopy techniques. In this lecture I will discuss about problems related to this spectroscopy. So, I will start with multiple choice question. First question is quite easy, that tells you about frequency if wavelength is given. So, question is calculate the frequency corresponding to the transition with a wavelength of your 56 nanometer. So, we know that frequency is related to c by lambda, where c is your velocity of light and lambda is your wavelength. Lambda is given, it is 56 nanometer, but it means that 56 into 10 to the power minus 9 meter. If we calculate this, we will get the frequency in per second, which is basically hertz. So, it is quite easy question, and if you do calculation, then what will you get is 5.4 into 10 to the power 15 hertz. So, this is the frequency of light of wavelength 56 nanometer. Now, let us go to second question. In this, you have to identify the region of electromagnetic spectrum where the wave number of given transition is 2000 centimeter inverse. So, these are the two energy states, and you have to tell that if wave number of given transition is 2000 centimeter inverse, then what is the region of electromagnetic spectrum. And this is this you have to know because the wavelength corresponding to 2000 centimeter inverse falls in IR region, and so answer is infrared region. The next question is what is the selection rule for rotational transition? What is the selection rule for rotational transition? There are 4 options: delta j is equal to 0, delta j is equal to plus minus 1, delta j is equal to plus minus 2, and D all of the above. We have already discussed this in our previous lecture. So, we know that selection rule for rotational transition is delta j is equal to plus minus 1. So, answer will be B. Next question is, upon isotope substitution of higher mass, what happens? Reduced mass increases, energy of transition level decreases, rotational constant decreases, all of the above. So, we need to know how to write reduced mass, and we know that reduced mass is m1 into m2 divided by m1 plus m2, m1 plus m2. And so, if we substitute an element with its isotope with higher mass, what we are going to get is your increase in reduced mass. And then we know that frequency of your transition is equal to 1 by 2 pi root k by mu. So, here your reduced mass will increase, and if reduced mass increases, your frequency will decrease. So, this is also right. And then about rotational constant, so B is equal to, so we need to know what is B, and B is your inversely proportional to your 1 by I, and since I relates to mu, you can also write 1 by mu, and so your B will decrease with increase in mu, which is reduced mass. So, basically all of the above, the D option is correct. Now, next question is, the rotational Raman transitions lie between two rotational levels, two vibrational levels, two electronic levels, and rotational and vibrational levels. So, if you remember rotational Raman transition, you will be able to answer this question very easily, and the answer is your D. Now, next question is, what is the selection rule for rotational Raman transition? So, the options given are delta J is equal to 0, delta J is equal to plus minus 1, delta J is equal to plus minus 2, and D is both A and B. So, answer is your delta J is equal to plus minus 2. I have discussed this in detail in the rotational Raman transition, and it was quite clear that why delta J should be equal to plus minus 2. So, answer is C. Now, you go to specifics of IR spectrum, and next question is based on that. Question is, the region of IR spectrum between 1400 to 600 centimeter inverse represents. So, these are the regions: fingerprint region, low frequency region, functional group region, and none of the above. And the answer is fingerprint region, and this is very important region if you want to get a structural feature of a molecule using IR spectroscopy. Which of the following molecule possesses IR active vibration? So, next question is based on the selection rule. You must know what is the selection rule for vibrational spectroscopy and rotational spectroscopy, and the things we know is that dipole moment of the molecule must change during the vibration. So, in this, the one which possesses IR active vibration is NO, because its dipole changes during the vibration. Now, next question is, identify which of the following is not a bending molecular vibration. So, there are 5 different kind of vibration is given. One is wagging, then twisting, stretching, scissoring, rocking, and we know that stretching is not a bending vibration. Stretching is not a bending vibration. So, answer is C. You have stretching, symmetric stretching vibration, this is your asymmetric stretching vibration, in plane bending. So, in plane bending can be of 2 types, scissoring and rocking. So, scissoring both are moving in towards each other, whereas in rocking there is like rocking between 2 different positions. Out of plane bending, and out of plane bending will be again of 2 types, and your wagging and twisting, the wagging and twisting. So, you must remember these different types of vibrational modes. In this, the wagging, twisting, scissoring and rocking are type of bending molecular vibration, while stretching is not. So, answer is C. Now, after multiple choice question, let us go to some problems related to rotational spectroscopy, and this is a question based on spacing between rotational lines. So, question is given, for a gaseous HCl molecule, the internuclear distance is found to be 143 picometer. If the rotational spectrum of HCl comprises of equally distanced lines, calculate the spacing between the lines. So, you have to calculate a spacing between the lines. What is given is internuclear distance. So, spacing between the lines is 2b, if you remember, where b is equal to h by 8 pi square IC. where B is in wave number unit. If we want to calculate the spacing between rotational line in Hertz unit, then the C will not be here. The spacing will always be equal to 2B. Only thing is the formula will differ. When you are expressing B in terms of Hertz, then there will be no C, but if you are expressing B in terms of centimeter inverse, then you need to write H into 8 pi square IC. So, 2B will be 2H divided by 8 pi square IC. 2H divided by 8 pi square IC. So, first thing we need to know is I, because H and C are constant and we know the value of H and C, and H is your 6.626 into 10 to the power minus 34 joule second, whereas your C is 3 into 10 to the power 10 centimeter per second. So, here I have calculated B in terms of centimeter inverse unit or wave number unit basically, and wave number unit can also be expressed either as meter inverse or centimeter inverse. If we are using meter inverse, then we have to express C in terms of meter per second. If we want answer in centimeter inverse, then we have to express velocity of light in centimeter per second. So, H and C are the constants whose values are already known. What we need to calculate is I, and for I you need to know reduced mass, which is mu. Mu is given by m1 m2 divided by m1 plus m2, and m1 m2 is given here. This is m1, this is m2, and you can calculate the reduced mass using this formula. One thing you must keep in mind that m1 is mass of one molecule, or mass of one atom. It is not mass of one mole of atom or molecule. So, what does that mean is that you have to express m1 in atomic mass unit, not in gram per mole. So, but if you suppose take m1 in gram per mole unit, then you need to divide that by Avogadro number. That will give you mass of one molecule or one atom, not 1 mole of molecule or 1 mole of atom. So, this thing you need to keep in mind, and then R you need to express in meter, and then you can calculate I is equal to mu r square. So, you can calculate moment of inertia using I is equal to mu r square. The mu already you have calculated, and r is 1.43 into 10 to the power minus 10 meter, and so your moment of inertia will be in kg per meter square. And once you put here in this equation, then you can get the value of 2B, which will tell you about the spacing between the lines, which is equal to 16.8 centimeter inverse. Okay, let us go to next question. In this question, you have to calculate frequency wave number of transition from the rotational spectra. So, question is, from a pure rotational spectrum of NO molecule, the bond length of NO is found to be 1.15 angstrom. Calculate the frequency corresponding to changes in rotational quantum number j is equal to 3 to j is equal to 4. J is equal to 3 to j is equal to 4. So, certainly we need to calculate B. For that, first you need to calculate the moment of inertia, and for moment of inertia we need reduced mass and bond length. Bond length is already given. So, first we need to calculate your reduced mass. So, reduced mass of NO will be given by mass of N multiplied by mass of O divided by mass of N plus mass of O. Here we are taking mass of 1 nitrogen, not 1 mole of nitrogen. Here you will take mass of 1 oxygen, and again this is mass of 1 nitrogen plus mass of 1 oxygen. So, this is 14 and 16 divided by 14 plus 16. We now need to divide by Avogadro number, because 14 and 16 gram is basically the weight of 1 mole of nitrogen or mass of 1 mole of nitrogen and mass of 1 mole of oxygen respectively. So, we need to divide by Avogadro number, and once we divide by Avogadro number, what we are going to get is your reduced mass in kg. First you will get reduced mass in gram, and then you divide by 1000, you will get reduced mass in kg. Now, we can calculate moment of inertia by using this equation. I is equal to mu into r square. R is already given, that is 1.15 angstrom, and that is basically 1.15 into 10 to the power minus 10 meter. So, you square this and multiplied by this reduced mass, you will get moment of inertia in kg meter square. So, now we know what is the moment of inertia. Now, let us go and calculate your rotational constant. Rotational constant in wave number unit is your h divided by 8 pi square I c. So, B is equal to h divided by 8 pi square I c. Here this is in wave number unit, wave number unit, wave number unit. If we want to express B in Hertz unit, then we need to just remove this C, this C. So, now we can go ahead and calculate B, since we know what is the value of H, what is the value of C, and what is the value of I. So, this is your value of H, this is what we calculated, and this is your velocity of light in centimeter per second, and so our B will be in centimeter inverse unit. If we take C in meter per second, then we will get the answer in meter inverse unit, and the answer is 1.96 centimeter inverse. And now we can calculate what is the frequency required for transition from j is equal to 3 to j is equal to 4. Now, again you keep in mind, sometime you write nu bar as 2 bj, and in some book you will find it is 2 bj plus 1, but that is not basically different, because when you express your nu bar in 2 bj, then I am talking about j value for the excited state, and when I say nu bar is equal to 2 bj plus 1, then the j is the value from value of the energy level from where transition is happening, So, here the value of j is 3, and so you can get nu bar, and nu bar will be 2 b into 4, b we have already calculated, and so nu bar is 15.68 centimeter inverse. Now, next question is basically to look at the effect of isotopes. Question reads as, if the bond length in both HF and DF molecule is same, and it is given as 0.053 nanometer. Now, we have to compare the value of reduced mass. So, when you are going from HF to DF and bond length is same, then what is the effect of isotope on reduced mass, moment of inertia, rotational constant, a wave number for the transition j is equal to 2 to j is equal to 3. So, let us go first calculate reduced mass. Mu Hf will be mass of one hydrogen atom multiplied mass of one fluorine atom divided by mass of one hydrogen atom plus mass of one fluorine atom. When you do the calculation, what you will get is 1.58 into 10 to the power minus 27 kg. Same calculation you can do for DF molecule, and the answer will be 3 into 10 to the power minus 27 kg. And so, you can just divide mu df by mu hf, and you can see what will the value of reduced mass for these two molecules. If you notice it, the mu df is almost twice that of mu hf. Now, let us go and calculate moment of inertia, and moment of inertia is given by mu r square, and r is taken to be constant and is equal to 0.053 nanometer. When you do the appropriate substitution, what you are going to get is moment of inertia in kg meter square, and this is your 4.44 into 10 to the power minus 48. And for df, it will be equal to, I think this will be almost double of that. This is wrong, so please correct it. Probably this is 8.88. You do the calculation, it is not very difficult. Why I am saying double? Because mu of IHF is half of mu of DF. So, please make the appropriate correction. Now, once we know the mu value and I value, we can go ahead and look at the rotational constant for these two molecules, and if you do a calculation for HF using B is equal to H by 8 pi square IC, you will get the B value for HF equal to 63.10 centimeter inverse, and B of DF is 33.24 centimeter inverse. 33.24 centimeter inverse. So, this is right. Now, you see that this rotational constant is inversely proportional to moment of inertia, and since moment of inertia of df is twice that of hf, and so B value of df will be half of B value of hf, approximately half of B value of hf, and that is what it is written here, that by using the concept that rotational constant is inversely proportional to reduced mass, we can calculate the B value of df. Since we know B value of hf, so we may not need to calculate this. We can simply use this formula BHF into mu hf by mu df. So, after the calculation of rotational constant for hf and df, now we will see what is the value of wave number for the transition j is equal to 2 to j is equal to 3. So, we can use this formula to know the wave number. Again, j is value of rotational level from where transition is happening, So, here transition is happening from j is equal to 2. So, j is equal to 2 here, and so you can calculate the 2b into j plus 1, and this is 2 into 63.1 into 3, and the answer is 378.6 centimeter inverse. For df molecule, same equation can be used, and then wave number what we get for j is equal to 2 to j is equal to 3 transition is 199.38 centimeter inverse. Again, you can see your nu bar df is half of nu bar hf, and that is not surprising because B of dF is half of B for HF. So, replacing H with D, mu gets doubled. So, I think this is wrong, mu gets doubled, whereas B and nu bar reduced to nearly half. Okay, so, now let us see another question based on effect of isotopes. So, question is, if the natural abundance of S218O in S216O is 1.3%, calculate the relative intensity of two rotational lines for the same transition in case of S216O. So, natural abundance of S218O is given 1.3. So, natural abundance of S216O can be calculated, and that is 100 minus 1.3, and that is 98.7. So, natural abundance of S218O is 1.3, and that should be equal to intensity for this S218O divided by intensity for S216O plus intensity of S218O multiplied by 100. So, I star is intensity due to S218O and I is intensity due to S216O. So, natural abundance of S218O is equal to your this is 16O, natural abundance of S216O will be equal to 98.7, and that will be equal to I divided by I plus I star into 100, and if you take the ratio of this I plus I star will get cancelled out. So, I by I star is equal to 98.7 divided by 1.3, and that gives you 76:1. So, for the same transition, rotational line for S216O is 76 times intense than that of S218O. Now, next question is calculation of atomic mass. The question is, for a diatomic molecule NX, the spectral lines are equally spaced in its pure rotational spectrum. If average value of spacing between the lines and the equilibrium distance of NX molecule are 3.551 centimeter inverse and 1.128 angstrom, and calculate the atomic mass of X. So, based on the rotational spectra, you can calculate the atomic masses, and this is one of the example. So, again first we will calculate the reduced mass, and reduced mass is mass of n multiplied by mass of x divided by mass of n plus mass of x into 1 divided by 6.023 into 10 to the power 23. So, this we are doing because we are taking Mn as molar mass. So, if we take Mn as molar mass, then we will divide it by Avogadro number. So, this is your Mn, you know that 14 into Mx divided by 14 plus Mx into 1 by 6.023 into 10 to the power 23, and this is equal to mu obtained from, let me see this, mu obtained from. So, the mu is what, 1.24 in 10 to the power minus 23. So, if you put it here, you can calculate mu mx is equal to 16.01, and since mx is equal to 16.01, so your molecule is NO and your atom X is oxygen, atom X is oxygen. So, the question 14 is that if you record the rotational spectrum of a molecule in which you do not know the atomic mass of one of the atom. So, here we are talking about diatomic atom, diatomic molecule, and what you do is you take a rotational spectrum, look at the what is the spacing between two lines, that will give you B. From B you can know I, and I will give you reduced mass if you know bond length. If you know bond length, and once you know mu, then you can calculate the mass of the other atom, which is x here. And what we showed you is that mass of the unknown atom is 16 gram, and that tells you that the x atom is your oxygen atom. Now, next question is calculation of dipole moment. I have not given a question, but I will show you one result from a literature how to calculate dipole moment of molecule using rotational spectroscopy. So, for that we know that in absence of electric field, the energy of rotational levels is given by this h square by 8 pi square I j plus 1, and j is rotational quantum number. And when you place the molecule in the electric field, then degeneracy is destroyed, and in that case for a linear molecule you give ER with this equation, ER with this equation. And if I plot ER versus E square, what I am going to get is mu square, which is basically here. Please do not confuse this mu with the reduced mass. This one is your dipole moment, dipole moment. So, if you plot ER versus E square, where E is your electrical field, you can get the dipole moment of a molecule, Okay. So, ER is basically delta ER is given by this value, and then delta nu is given by this value. So, delta nu is basically delta ER by h, and you can see that it is 2 h square, here it is 2 h. And when I plot delta nu versus E square, I can get the value of dipole moment, where mu is your dipole moment. So, I am showing you the calculation done in a paper. This is paper from PCCP that is published in 2005. They calculated the dipole moment of anisole and benzaldehyde, and here you see delta nu versus E square. That is what we generally plot to get the dipole moment, and they have calculated dipole moment. They have calculated dipole moment using this plot. Similarly, this is for anisole and this is for benzaldehyde. So, this is the way to calculate your dipole moment of a molecule using the splitting of rotational lines in electric field which is known as Stark effect. Now, next question is from rotational Raman spectroscopy. So, what is the separation between spectral lines in rotational Raman spectrum? We know the separation between spectral lines in rotational spectrum, and that is equal to 2b. Now, we are going to see what is the separation between spectral lines in rotational Raman spectrum. So, this is your energy of the rotational levels, Fj is equal to Bj j plus 1. Now, if you take F in Hertz unit, then B will be in Hertz, and if you take F in centimeter inverse unit, then B will be in centimeter inverse. So, this F is given by Bj j plus 1, and let us take this in centimeter inverse, then B is in centimeter inverse. Now, selection rule for rotational transition, rotational Raman transition are delta J is equal to plus minus 2, that I have already discussed. So, let us calculate nu bar. Nu bar is your wave number for transition between J to J plus 1 level, J to J plus 1 level. So, that is given by f j dash, this is, let us take this as a j dash. So, f j dash minus f j, and if you take j dash, for j dash you can write b j dash plus 1 minus b j plus 1, and j dash will be j plus 2, because your selection rule for rotational transition delta j is equal to plus minus 2. So, your nu bar is b j dash plus 1 minus b j plus 1, and if you take b out, this is the expression, and we know that j dash is equal to j plus 2, because that is what is the selection rule for rotational Raman transition. So, let us write rotational Raman transition, and so nu bar is equal to b j plus 2, for j dash you put j plus 2, j dash plus 1, j plus 3 minus j plus 1, and what you get is this equation 4b j plus 3 by 2, j plus 3 by 2. So, since j is equal to 0, 1, 2, 3, so j increases by 1, and so a spacing between spectral lines of rotational Raman spectrum is 4b. So, the separation between spectrum lines in rotational spectrum is 2b, whereas separation between spectral lines in rotational Raman spectrum is 4b. Now, next question is based on vibrational spectroscopy. For a diatomic molecule CO, the force constant is 1906 Newton per meter. So, you need to calculate what is the fundamental vibrational frequency in centimeter inverse. Again, first we have to calculate mu. I have discussed calculation of mu several times, so I am not going to discuss it again. The value which you obtain for mu for CO molecule is 1.138 in 10 to the power minus 26 kg. So, fundamental frequency will be your nu bar is 1 by 2 pi c root k by mu. Again, the wave number can be, so this is wave number, so it will be in meter inverse or centimeter inverse unit. So, just put the values 1 by 2 pi c is your 3 into 10 to the power 10 centimeter per second inverse. So, please correct this, this is centimeter per second inverse, and this is your k, which is force constant, it is given 1906 Newton per meter, and this is your reduced mass which we just calculated for CO molecule, and what we will get is wave number to be 2172.2 centimeter inverse. Now, next question is what will be the spacing in electron volt between vibrational energy level of a CO molecule if the force constant is 1748 Newton per meter. Now, we are going to calculate the frequency of vibrational transition. Again, we will calculate mu just we calculated for CO, this is 11.4 into 10 to the power minus 27 kg. So, frequency of the vibrational transition is your, this formula we have already discussed, and that equal to 2078 centimeter inverse or 2078 centimeter inverse, and this we can convert into delta E. Delta E and your nu bar is related by this equation, 1 electron volt is equal to 8066 centimeter inverse, and so delta E can be calculated by dividing 2078 with 8066 centimeter per electron volt, and what you are going to get is 0.258 electron volt. So, this is your spacing between the vibrational levels of CO molecule. Now, next question, in this 35Cl molecule is a 35Cl molecule is irradiated with a mercury lamp of a wavelength of 443.6 nanometer. If the fundamental vibrational frequency for the molecule is this second inverse, what we need to calculate is what is the Raman line in nanometer, okay? Stokes Raman line. The frequency of mercury light can be calculated using this formula, nu is equal to C by lambda. C again we have taken in meter per second, and you can express lambda in meter, and then we can get frequency in second inverse, and so Stokes line will be observed at nu frequency of incident light minus frequency of vibration. Here it is a fundamental vibrational frequency. We have just calculated what is the frequency of incident light, and that is 67.63 into 10 to the power 13 second inverse, and then fundamental frequency is given. So, you just subtract this from frequency of incident light, and you can get frequency of the Stokes Raman line, and that is equal to 62.234 into 10 to the power 13 second inverse. And you can also calculate wavelength of Raman by using this. We know that frequency and wavelength is related by this equation, C by nu, and so you can calculate what will be the wavelength of Stokes line, Raman line, Stokes Raman line. Okay, so next question is identify the allowed vibrational transition for a diatomic molecule, and again this is based on selection rule. So, you know that for allowed vibrational transition delta V is plus minus 1, and so first is not allowed, second is allowed, third is allowed. Okay. In the B it is delta V is equal to plus 1, and here delta V is equal to minus 1. Okay. So, next question is basically to calculate dissociation energy using vibrational spectroscopy. Just before going to discuss that question, I will like to have recap for anharmonic oscillator. So, energy of vibrational levels for a anharmonic oscillator is given by this equation, where V is vibrational quantum number, and if you try to express this in wave number unit, you need to divide by SC, and that is generally given by this symbol GV, and that is basically V plus half omega E minus higher wave number term. So, now you have wave number, you can calculate the difference between 2 in wave number unit, and when you 2 vibrational level from V to V plus 1. So, if you calculate the difference between this vibrational level in centimeter inverse, you are going to get this formula. So, G V plus 1 minus G V is equal to omega E minus 2 x E omega E V plus 1. And so, if we plot this versus V plus 1, then we can get x E and omega E, x E and omega E. Okay. And now, let us think of how to calculate the vibrational level with maximum energy. And if I want to calculate the vibrational level at which energy is maximum, then I need to differentiate that and put that equal to 0. When you do that, you will get V is equal to 1 by 2 x E minus half. And if you put this in this equation and then you subtract by your 0 point energy, what you are going to get is D. This I have explained in detail in the last lecture. I have explained this in detail. but what I showed you that d is equal to omega e minus divided by 4 x e omega e. So, after this recap, let us see this question. The question is, the fundamental and first overtone transition are centered at 1876.06 centimeter inverse and 3724.20 centimeter inverse respectively, and you have to calculate these 5 parameters. So, let us first start with fundamental absorption. Fundamental absorption frequency is given by wave number is given by this omega e multiplied by 1 minus 2 x e, and that is given 1876.06 centimeter inverse, and for first overtone wave number is given by this equation. So, for first overtone wave number is equal to 2 omega e multiplied by 1 minus 3 x e. So, you have these two, and so you have two equations and two unknowns. Unknowns are omega e and x e. So, you can solve these two equations to get the value of omega e and x e. Easiest way to do it, divide 1 by 2, and when you divide 1 by 2 you can get the value of x e, and when you put x e in one of the equation, then you can get value of omega e. So, it is simple calculation, you can do it easily. So, please do it. Now, once you know that what is the value of omega e and x e, you can calculate G 0, which is basically 0 point energy, and the 0 point energy is given by this equation. This equation has already been discussed in the last lectures, last 2 lectures. So, please just go and see these equations. So, what now I do is I just plug in the value of omega e and x e, which I obtained in the previous slide, and when you do that you will get the value of G naught, which is basically the 0 point energy. Now, you can use omega e to get the value of k. Basically, you have to calculate k because you know mu, reduced mass is known. So, reduced mass is basically this, and omega e we have already obtained. So, we can get the value of force constant. So, if you remember the question, the fourth point is to calculate force constant, and that is what we are calculating, and force constant is 1.593 into 10 to the power 3 meter inverse. Now, we need to calculate your dissociation energy. For that, I told that first you have to calculate the vibrational level with maximum energy. So, you need to find out the value of V at which the energy is maximum, and this is the formula for V max, and once you solve that you will get V max is equal to 68. Now, we will put the value of V max in the equation for G V. When we do that, we will get G max. So, G max is V max plus half omega e and 1 minus V max half x e, and when you solve this you will get the value of G max, that is energy of the vibrational level whose energy is maximum, and it is given in centimeter inverse. And you can calculate E dissociation. E dissociation is basically G max minus G 0 into S C. S C is multiplied since this the G value is in centimeter inverse. So, if you multiply it by S C, then you can get the energy in joule unit. So, this is your dissociation energy in joule. Now, let us go to some application based questions, particularly in vibrational spectroscopy. So, here first question is, how does conjugation to the carbonyl group affects its IR stretching frequency? Conjugation weakens the carbonyl pi bond. So, you can see that if we look at the resonance. So, this will get a double bond and that will get a partial single bond. So, conjugation leads to weakening in carbonyl pi bond, and that decreases the value of K, it decreases the value of K, and so frequency of CO bond decreases. So, on conjugation frequency of CO bond decreases. Now, we will look at how does IR stretching frequency of carbonyl group in cyclic ketone increase with decrease in number of carbon. So, what happens that when number of carbon in cycle increases, then ring angle decreases, and that affects the frequency. So, ring strain increases with decrease in ring angle. So, here there should be increase. So, as the number of carbon increases, ring angle increase. So, if I going from this to this side, your ring angle decreases, and once ring angle decreases, ring strain increases with decrease in ring angle, and so energy and thereby nu for CO bond increases. So, in this question what we are going to look at, can we apply vibrational spectroscopy to distinguish between position of keto group, position of keto group. So, here is aryl alkyl ketone and here is dialkyl ketone. So, now you see that this one is involved in conjugation with the ring, benzene ring, and we know that on conjugation this K decreases, and if K decreases, your frequency will also decrease, and so frequency of CO stretching in aryl alkyl ketone comes at a smaller wave number in comparison to dialkyl ketone. So, conjugation weakens the carbonyl pi bond. Now, again we will see another example. We want to distinguish between the position of keto group, and this is your 2,4-heptane dione. This is 2,4-heptane dione and this is 2,5-heptane dione. Can we distinguish between these two? So, here you see this is this CH is basically between two CO group, and so here H is acidic, and so this can exist in enol form, this can exist in enol form, and if it exists in enol form, what will happen is you will have a peak for OH stretching, which will come around 3200 centimeter inverse, and your frequency for CO will be at a smaller value, because here K for CO will be small. Whereas, this conjugation, this enol formation is not possible in this structure, and so your nu for CO will be at 1700 centimeter inverse, and there will be no peak for OH stretching, no peak for OH stretching. So, now next question is, can we distinguish two esters? The example of methyl benzoate and phenyl acetate, and now you see that here there is conjugation between these two bond, and in this there is conjugation with the lone pair. So, due to conjugation on O group, here frequency will be at 70-60 centimeter inverse, whereas nu for CO stretching in the above case will be at 17-10 centimeter inverse. We can also distinguish between nitrile and isonitrile using vibrational spectroscopy. For nitrile compound, the frequency for C triple bond N stretching will be at 2275 centimeter inverse, whereas nu for this isonitrile will be at 2180 centimeter inverse. So, using that you can distinguish between nitrile and isonitrile. Mono and polyalkylated polysubstituted alkyl halide, mono and polysubstituted alkyl halide can also be distinguished. For example, 1-chlorobutane and 1,1-dichlorobutane can be distinguished by IRS spectroscopy. Here frequency will be at lower wave number when you have only one Cl, but if you have two Cl, then this frequency will increase to 790 centimeter inverse. So, you will be able to distinguish between mono and polysubstituted alkyl halide. Okay, so, next question is how we can use IR spectroscopy to distinguish between ortho and para nitrophenol. So, you know that in ortho nitrophenol, the hydrogen of OH group in phenol is in hydrogen bond with nitro group, and that basically leads to broadening of band. So, wherever there is a hydrogen bond of OH group, there will be a broadening, and this broadening will be observed between 3500 to 3100 centimeter inverse. In para-nitrophenol, the hydrogen bonding is not possible between this hydrogen and this nitro group, and so you will get a sharp band corresponding to OH group at 3350 centimeter inverse. So, ortho and para-nitrophenol can be distinguished using IRS spectroscopy. So, in this lecture, I have looked at several different kind of questions. Some are multiple choice questions and some are problem based questions, and some is application related questions. So, there are a lot of different kind of application we can think of between rotational applications of rotational and vibrational spectroscopy. In the next lecture, I will start with your atomic spectroscopy. So, thank you very much for listening. The books, I have already told you which books I am using it. For example, in organic spectroscopy, I am taking help of William Kemp book on organic spectroscopy, which is from Palgrave publication, and these two are for physical spectroscopy, and this is one basic book on your chemistry, basic book on chemistry. So, thank you very much and thank you for listening.